Okay, let's dive in. We've got this material you send over on squares and square roots, and we're going deep.
Right.
The plan is to really cut through it, find the core ideas, maybe pull out some, surprising bits you might have missed. It's like a quick way to get up to speed.
Exactly. We're boiling down what's key in these notes. So starting right at the beginning, what actually is a square, mathematically speaking?
It's just a number times itself. Right?
Yeah, simply multiplying a number by itself.
Right.
Like 5 times 5 is 25, and the notation is 5 with a little 2.
Five-atary, yeah, that exponent.
Oh.
And the square root, that's just the flip side, isn't it?
Mm-hmm.
It asks what number times itself gives you the original number. So
Yeah.
like 36 is 6.
Because 6 squared is 36.
Yeah.
Yeah. And the notes mention the symbol, the radical sign.
Oh, yeah?
It actually comes from the Latin word radix.
Which means root? Huh. Kind of cool.
It is, and what jumps out straight away from the properties in the material is how predictable squares can be sometimes.
Like with even and odd numbers.
Exactly. You square an even number, like 2, you get 4. Or 6, you get 36. The answer is always even.
And same pattern for odds. 3 squared is 9, 7 squared is 49. Always odd. Seems basic, but it points to something deeper.
It really does, because, an even number is always 2 times something, say 2n. Square that.
2n.
You get 4 and 1, which has to be even. And an odd number, that's like 2n plus 1.
Right.
Square that, you get 4n mental plus 4n plus 1. The first part's even, add 1. Makes it odd. It's quite neat how it works out.
It is neat. Okay, another big point from the material. Positive or negative, doesn't matter. When you square it,
Always positive.
always positive.
Yeah.
Three-dimensional lines, sure, but MEDIC 3 OSO is also 9.
And that has a big implication for square roots, doesn't it?
Yeah, what's that?
Well, if squaring any number gives you a positive, then you can't really find the square root of a negative number, not within this set of rules anyway.
Oh, right. Because no number times itself will give you a negative. Makes sense.
Okay, so moving on to perfect squares.
These are the nice ones?
Yeah, the ones where the square root is exact, like a whole number or maybe a clean decimal.
So 16, its root is 4. 49, root is 7. The notes even mention 1.21.
Root 1.1, exactly. And the material highlights a really handy way to check if a number is a perfect square. The prime factor method.
Okay, how does that work?
You just break the number down, all the way down to its prime factors.
Like its basic building blocks.
Precisely. And if every single one of those prime factors can be paired up,
Like Noah's Ark. 2 by 2.
kind of, if they all have a partner, it's a perfect square. Take 196.
Okay.
That's 2 times 2 times 7 times 7. See? A pair of 2s, a pair of 7s, all paired.
So 196 is a perfect square. But what about 180?
Good example. 180 is 2 by 2 by 3 by 3 by 5.
Okay, pair of 2s, pair of 3s, but the 5 is left over.
Exactly. That lone 5 means 180 is not a perfect square. Its prime factors tell the story.
And you can find the root this way too, the notes say.
You can. Like for Shiv and 484, the factors are 2 by 2 by 11 by 11.
Pairs again.
So you just take one factor from each pair. 1, 2, 1, 11. Multiply them.
2 times 11 is 22. So the square root of 484 is 22. Clever.
It's a neat method. The material also mentions the division method, especially for bigger numbers or decimals. We won't get into the weeds on that one now, but it's another tool.
Right. And speaking of decimals, there's a really specific property mentioned.
Yes, the number of decimal places.
When you square a decimal, the result always has an even number of places after the point. Like 0.3 is 0.09. That's 2 places.
Or 0.015 mullet, that comes out to 0.0000225. 6 places. Still even.
So this means a decimal can only be a perfect square if it has an even number of digits in its decimal part.
That's the rule. And the notes explain you can use that division method for non-perfect square decimals too, by adding pairs of zeros to get the accuracy you need.
Now this next part was fascinating, just looking at the last digit of a number.
Yeah, some real shortcuts here. The material points out if a number ends in 2, 3, 7, or 8.
Then right.
It just cannot be a perfect square, period.
Wow. Okay. That eliminates a lot right away.
It does. And there are more patterns. If a number ends in 1 or 9.
Its square ends in.
1. Think 9 to round 81, or maybe $11 121. 19 double 361. Always ends in 1.
And numbers ending in 4 or 6.
Their squares always end in 6. Like 4 and dozen, 16, 6 to 3, 36, 14, 7 and 96, 86. Ends in 6.
Okay, one more digit pattern. Zeros.
Right. If a number ends in, say, n zeros, its square ends in double that, 2 n zeros.
So 30 ends in 1 0, 30 plus and 1 is in 900, ends in 2 zeros.
Exactly. 300 ends in 2 zeros, 300 butters, 90,000 ends in 4 zeros.
Which means
Okay.
if a number ends in an odd number of zeros.
Can't be a perfect square because you can't get an odd number by doubling something.
These patterns are pretty powerful. And there was that word problem example, the orchard.
Yeah, the farmer planting 5,625 trees, wanting the same number of rows as trees per row.
That's literally asking for the square root of 5,625.
It is. And the square root is 75. So 75 rows is 75 trees in each. It's a direct application.
So wrapping this up, what's the big picture? We've covered the basic squares, roots,
Looked at how squaring works with even odd numbers, positives and negatives.
how to spot perfect squares with those prime factor pairs.
Mentioned methods to find roots, saw the rules for decimals, and those last digit tricks.
It really gives you a toolkit for understanding these numbers better.
It does, and maybe here's something to chew on, thinking about those decimals again.
Don't.
We saw that a perfect square decimal has to have an even number of digits after the point. Why? Like, mathematically, why is that rule so absolute? What's actually happening when you multiply a decimal by itself that enforces that even number of places rule?
Huh. That's a good question to leave things on. Why does that structure hold? Something for you to think about.